We'll focus on some more complex algebraic expressions in the future, but for right now, I want to show you just kind of what this process is going to look like of evaluating that instantaneous rate of change expression that we wrote in the previous video. So let's just take a look at a different function. I want us to be able to verify a result that we already know is going to be true. So we know the linear function. The linear function f of x equal to 3x minus 7 has a constant rate of change or slope of 3. You know that from your very first algebra days. This line has a y-intercept of -7, slope of 3. You could graph it in your sleep. But what I really want us to focus on, if we know that it has a constant rate of change, meaning that at any given point, the rate of change at that point is 3, then the expression that we wrote in the previous video should work and should come out to 3. So let's write that expression. We're going to write an expression to evaluate the instantaneous rate of change at x equals 5. So again, we're looking at a point here at x equals 5. And we already know that no matter what x I gave it, I could have said x equals 2 or x equals -10, but that we already know, because it has a constant rate of change of 3, that the instantaneous rate of change at this point also we can verify that it equals 3. So let's build our statement earlier. Well, we said that instantaneous rate of change can be found by finding the limit as h approaches 0 of f of a plus h minus f of a over h. So let's let our point, we're looking at x equals 5, so I really want to know what is the limit as h approaches 0 of f of 5 plus h minus f of 5 all over h. And what this is going to come down to, and what this process is going to look like with some more complex functions that we'll be looking at, is I need to know what f of 5 plus h is, and I need to know what f of 5 is. So let's evaluate those things. F of 5 plus h means to take 5 plus h and substitute it in for x, minus 7. And if I distribute the 3, I get 15 plus 3h minus 7. And so if I combine the 15 and minus 7, I get 3h plus 8. So that's what f of 5 plus h is. F of 5, well, that's just going to be 3 times 5 minus 7, which is 15 minus 7, which is 8. So if I plug these back into this expression right here, take a look at what I get. I get the limit as h approaches 0 of f of 5 plus h, which we said was 3h plus 8, minus f of 5, which was 8, all over h. And then I can simplify the numerator. 3h plus 8 minus 8 is equal to the limit as h approaches 0 of 3h over h. And then, as we saw when we evaluate limits, I can divide out common factors and say the limit as h approaches 0 of 3, and we know the limit of a constant is just equal to that constant value 3. So you can see this expression verified that, yeah, the rate of change at x equals 5 was in fact 3. And you could do this exercise with any given value of x. Because we're talking about a linear function, it would always come out to be 3. The really interesting result is that when we start looking at this with nonlinear functions, we'll get a numeric answer as to what the actual rate of change is at a given point of all types of functions that we'll look at.